In this particular video, we're going to talk about uh, another problem. It's called parallel ranking, and this is an example that I found on this particular website, and we're going to use this particular example to study MPI Gather and Scatter operations. So what exactly is a parallel ranking? The problem description is like this. So we have a bunch of processes. Here we have like 4 processes, and on each of the process in its own local memory, we have one number. Right? So on rank 0, we have a number 5. On rank 1, we have a number 2. And then on rank 2, we have number 7. And then on rank 3, we have a number 4. And the problem is that for each of the process, the process would like to know the overall ranking of its own number among all those numbers that's been distributed on the entire cluster. Right. So in this particular example, the rank 0 has a number 5, right? So 5 ranks at. So we have like 4 numbers, right? So 2 is the smallest number, then so its ranking is 0. 4 is the next smallest, so the ranking is like 1, and then 5 is the next smallest, so then its ranking is 2, right? So the result is like a rank 0 would like to have a number 2, which actually indicates the overall ranking of its own number, in which case it's 5 among all those numbers. And then rank 1 has number 2, right? 2 is actually the smallest number among those 4 numbers. So rank 1 would like to get a number that's 0, that indicates the overall ranking of its own number 2 among all the numbers. And then rank 2 has a number 7. 7 is actually the biggest number among the 4 numbers, right? So the ranking of the number 7 among the 4 numbers is 3, right? So the result on rank 2 should be like 3. And then rank 3 has a number 4, right? And 4 actually ranks like a 0, 1, right? So that's the second smallest. That's the second smallest number. So 3 would like to get a number that's 1. Right. So in this particular problem, we cannot confuse the ranking of the number with the rank of the different processes. The rank for the different processes is a unique ID for the different processes in a cluster, right? In a parallel calculation, right? But the ranking of a particular number is basically the order. If you actually sort all those numbers, and then what's actually the 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 rank of one particular number, that's the ranking that we're actually sort of talking about, right? And the basic workflow is like that. The basic workflow that we would like to implement is like this. So at the beginning we have like 4 different numbers distributed on 4 different nodes, right? So we would like to gather all those 4 numbers into just one node, into the root rank 0, right? 0 into like one into one rank. So what we would like to do is to collect all those 4 numbers and then transfer them onto just one rank. In this case, it's rank 0, right? And then on rank 0, we need to attach the ownership information. So basically, we need to know uh, each number is actually coming from which rank. So in this case, the number 5 actually comes from rank 0. And then the number 2 actually comes from rank 1. And then the number 7 actually comes from rank 2. We'd like to attach this ownership information to each of the number. Right? And then on rank 0, because we have all those numbers, we can sort them. We can sort them according to the value of the numbers. Right? So after sorting, we have this kind of order, right? Number 2, number 5, number 4, number 5, number 7, right? And then after sorting, the owners also are somehow sort of attached, because the owners are attached to the number, so the owners have a particular order, right? So owner 1 is at the beginning because its own number 2 is the smallest, and then owner 3 is the second one because its number 4 is ranked at the second, right? And then we would like to collect all those 1, 3, 0, 2, this ordering information into one array, basically assign ranks by owner. So rank 0. So the owner 0 is ordered at 0, 1, 2, right? So owner 0 is at position 2, and then owner 1 is ranked at position 0. It's at position 0, and then owner 3 is at position 1. Uh, so owner 3, that's 1, right? And then owner 2 is at position 3. Owner 2 is at position 3. And then once we got this array, we would like to sort of distribute all those numbers to different rank, to different to the different processes, and this is called a scattering operation, right? So 2 goes to rank 0, 0 goes to rank 1, 3 goes to rank 2, and then 1 goes to rank 3. And the basic operation that we're gonna talk about using this particular example is called gather, right? First we have to gather all those numbers from the different rank. So gather is an operation that looks like that. So rank 0 has a red box, rank 1 has a green box, right? And then the gathering process is going to transfer all those different numbers from each of the different ranks in your process, each of the different processes in your communicator, or to a root communicator, to a root process. So on root 0, on rank 0, we're gonna get all those boxes. And the syntax is more or less like that. So it's quite long. It's quite long, right? But it's not too difficult to understand. So the first input is the send buff. It's the send buff. It's basically the storage on each of the different processes that you want to send to the root. That's the send buff. It's basically the green, the red, the green, the blue, and the cyan boxes on each of the different ranks, on each of the different processes. And then send count. So how many numbers are you actually sending in each of the send buff? And then the data type. And then you're gonna have a receive buffer. This receiver buffer is basically a storage on your root rank, in which you want to store all those different data that's coming from all the different processes. So it must be big enough to hold all those data that's coming in. And then receive count, it's basically how many numbers you are expecting from each of the, how many numbers you are actually expecting from each of the source processes, right? It's not the total number. It's not the total number. It's not 4. In this particular example, the receive count is also 1 basically. And then data type again, and then the root process, the root rank. So in this particular example, the send, this is actually an example. This part of the code is actually an example. So send ARR is the send buffer, and it's 100 integers, right? And then the root rank is 0, and then we have a receive buffer. So the receive buffer in this case is a pointer. It's a pointer to a int. It's an int pointer, basically. It's an integer pointer. And then m processes is basically just the total number of processes in one calculation, in one particular calculation. You can sort of see its get size. It's the output of the get size. So that's the total number of ranks, total number of processes. And then receive buffer. Here we're actually allocating storage for receive buffer, right? So each of the process is going to send over 100 integers, and we have m process this many processes. So the storage is going to be the total number integers we're going to receive is this m processes multiply 100 basically. So that's m processes multiply 100, and then multiply the size of int, and then the whole thing is actually the storage that we want to allocate. That's why we're putting a new here, right? And then when we call the gather, send ARR, that's the address of the send buffer. And then 100, it's the number of integers we are sending from each of the individual ranks. And then the type, it's int. And then receive buffer, that's the address of the receiving buffer, RECV buffer. And then 100, that's the receive count. we're expecting 100 numbers from each of the individual ranks, and then the type is int again, and then the root is uh, the rank of the root process. So that's basically how you can actually use the gather, MPI gather, to actually collect all those different informations. And then another calculation we're going to need is called scatter. Scatter is just like the opposite of gather, right? Scatter is just like the opposite of gather. So here we have a root process that has like 4 different numbers, and a scatter means that I want to distribute those different numbers to different processes. That's called a scatter. And we have to sort of pay attention to the difference between a scatter operation and a broadcast broadcast communication. Both of them are collective communications and must be called by every rank in a communicator, but they actually perform different kinds of operations. So in a broadcast, you're actually sending the same information to all the ranks. So here it's a red box on root 0, on rank 0, and then you are actually copying duplicating the same information on every other rank, basically. But in a scatter operation, it's a kind of different thing. So on the root rank, you have 4 different pieces of information, and then you are actually sending different pieces to different process, and that's called a scatter, right? So how do you actually use the scatter function? How do you actually use the scatter function? It's quite similar to the gather function. So the first input is the address of the send buff, and the send buff is supposed to be allocated on the root rank, right? So that's the piece of data, that's the data that you want to send out to each of the different processes. And then send count how many numbers you're actually sending out to each process. It's not the total number. It's not 4, it's 1 in this particular example, right? Because you are sending 1 number to each process, right? And then the data type, and then um, the address of the receive buffer, right? So on each of the different individual ranks, you must allocate sufficient memory to actually receive the data that's coming over from the root rank, right? And in this particular example, the receive buffer is just a 1 because you only have like a 1 number that's coming to each of the processes. And then receive count, in this particular example, it's 1, right? How many numbers you are expecting to receive on each of the different individual ranks. And then data type, it's a int, and then the root process, which is 0 in this case. So let's look at one example. That's the example code, right? So receive array is like 100, right? So on each of the rank, I have an integer array with like 100 numbers, right? That's going to be our receive buffer. And then the root is going to be 0, and then there's a send buff is going to be allocated on just the root rank. That's going to be 0 rank, and then here it's actually allocating the total storage. So on the root rank, we're going to allocate send buff, which is the total number of processes multiply 100, because each of the individual rank is expecting 100 numbers, and m process is the total number of processes in the calculation. Then the total number of storage we have to allocate is just basically m process multiply 100, and then the size of int, and then we allocate this much data on the root rank, and then we just call scatter. So the address of the send buff, we're sending out 100 numbers to each of the rank, and then it's going to be int, and then receive AR, that's the receiver buffer, address of the receiver buffer. So each of the individual rank is expecting 100 numbers to receive 100 numbers, and then it's going to be integer, and then all those data are coming from the root. So now let's look at how we can actually solve this parallel ranking problem by using the gather and the scatter operations. And let's start to write our code. So I'm gonna create a new directory. Let me exit the editor first. Right. I'm gonna create a new directory that's called parallel rank. Right. And then I'm gonna go into this then let me recreate the directory. The reason I'm having trouble is because I have a file that's already named the parallel rank. Uh, parallel rank. That's what I'm supposed to do, I guess. And then Emacs NW parallel rank.cpp. So let's try to write our code for solving this problem. And some boilerplate codes. Bits std c++ dot h, and then include mpi dot h, and then using namespace std. So we are going to generate some random numbers on each of the different ranks, right? And then we are going to need a function for generating random numbers. So let's first write a function for generating random floating point numbers. In a previous video, I was just using the C++ included file, included function for generating random numbers that's called rand. But it seems that this kind of function is not this particular function is not really will not actually generate truly random numbers. So the 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 new way of generating random numbers is slightly different than before. So I'm gonna use the latest sort of the, the best way of generating random numbers. Uh, I'm gonna write a function following this new standard. I'm gonna call my function get random float. So it's a function for generating random floating point numbers. So I have to random device rd. So that's the first thing I'm gonna need. And then there's an engine that's called 19937. So MT19937 is a random number generating engine. Right. It's got multiple choices, but looks like this one seems to be quite popular, so I'm gonna use this one. And then I'm gonna need a uniform real distribution. Uniform real distribution. So it's a templated function. I'm gonna call this dist. And then the uniform distribution is gonna go from 0 to 1. So I'm basically trying to generate floating point numbers from between 0 and 1. Random floating point numbers between 0 and 1. And then it's gonna return dist, giving it the random number generating engine. And that's going to be our function for generating random floating point numbers that's uniformly distributed between 0 and 1. And then now let's try to write our main function. And then I'm going to initialize MPI. And then I'm going to finalize my MPI. And then I'm going to get the size of the communicator. I'm going to get the rank. And then I'm going to define my MPI root to be the process with the rank of 0. So on each of the process, we need to get a random number, get a random floating point number. So I'm gonna introduce one variable, v. So v is gonna be our random number. It's gonna get random float. So this v actually exists on different processes. So every different rank is gonna have a different value for the v. Right, because it's actually calling the get random float, and every time this function gets called, it's going to generate a different floating point number, and we're going to store that into v. right? So before we actually do anything else, let's look at our random numbers. So rank, MPI rank, and then random float. Let's take a look what's actually the random numbers being generated. So let's compile it. MPIC. We're going to use 8 processes. So we're going to generate 8 different random floats. So you can sort of see rank 0 has a random float that's 0.2 something. And then rank 1 has a random float that's close to 0.8. So you can sort of see every different rank actually owns a different floating point number. So what we are going to do is to actually sort those floating point numbers. So we're going to sort of gather all those floating point numbers to rank 0, sort them, and then the ranks are going to be assigned back. The ranking of those numbers are going to be assigned back to each of the different processes. So here we have the floating point numbers, random floating point numbers that's been generated, right? Um, so let's define 2 vectors. So this vector floats is going to be used for storing the gathered floats from each of the rank. Gathered floats. And then we're going to need another float, a vector of ints that's going to store the ranking of all those floating point numbers. Let's call it float ranks. The ranking of all those different floating point numbers. So this rank is not the same as this rank, right? This rank is basically the unique ID of the different processes in our communicator. But this rank is actually the order of the different floating point numbers once we actually sort them. Um, and these gathered floats can have just the 0 size on every core except on the root process, right? On every other process that's not the root process, these gathered floats can hold just the 0 numbers. But on the root process, these gathered floats must be allocated because later on we're going to transfer all those different floating point numbers from every other rank to the root rank. So if MPI rank actually is equal to MPI root, then we have to allocate space for gathered floats. So gathered floats, we're going to use the resize function. We're going to use this resize function, and the size is supposed to be the same as MPI size. So if we have this many different processes in our calculation, then the gathered floats should be as large as this number. So we're going to allocate it. So once we have allocated the space for this particular vector floats, we can do our gathering now. Don't forget, a gather operation is a collective operation, which means that it must be called by every rank in your communicator. So that's why our gather call is not inside of this if branch, it's outside of it. So MPI com world dot gather, right? So the send buffer, that's the address of V. That's the float that we're actually sending from each of the different ranks. And then the count is 1. It's MPI float. That's the type. And then the receive buffer is going to be the address of gathered floats 0. Don't forget, the gathered floats has allocated spaces on the root rank, but it doesn't really have any spaces on every other rank. So, but it's okay. In this case, it's okay. And then another count MPI, another type, and then we must tell MPI, which is the root process. The root process is going to have a rank of 0, and that's it. That's the gather. So after we have finished gathering the data, let's do a print. So 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 if MPI rank actually equals to MPI root, let's print out. Let's just print out the gathered numbers. So I'm going to use a range for if inside of gathered floats. I'm going to do a cout f, separate them with space, and then cout end of line. So let's see what's going to be the results. Right, let's just make sure our gathering operation is done correctly. Let's see if we actually did the gathering right. Right, so the first number is from rank 0. It's supposed to come from rank 0. Rank 0 has a number that's 0.104661, right? 0.104661, right? And then second number is supposed to come from rank 1, right? Rank 1 has a number 0.166142, 0.166142. And then the third number is supposed to come from rank 2. That's 0.228959, 0.228959. It looks like we have done the gathering correctly. So let's go back to our code. So once we have finished gathering all the numbers, we are at the second step now, right? We have finished gathering the numbers to the root, right? So now root 0 has all the floating point, all the random floating point numbers. That's 8 numbers, right? And now we have to attach ownership information to each of the numbers. So so let's look at how we can actually do that. So I'm gonna introduce another vector. This vector is gonna have so the type of the elements inside of the vector is gonna be a pair. So pair is actually a C++ type. It's a C++ type, and it's also templated type. So a pair is just for it's a type that's for storing just some kind of a hash map. You have a key and then a value, that kind of thing. And in our case, we're having the pair is composed of 2 numbers. One is an int, which is going to be used to store the rank of the different processes, and then the second one is a float, which is going to be used for storing the random floating point number, right? So that's going to be our float, and then we're gonna that's going to be our vector. We're going to call it rank float pairs, and then um, we're going to do a loop and then try to sort of put those pairs into this particular vector. So we're going to do a loop for I'm going to my counter is going to be called rank. So rank goes from 0. So rank is going to be smaller than MPI size, and then rank plus rank. And then rank float pairs dot pushback. So we're going to push back a pair. So how do we actually make a pair? There is a function that's called a make underscore pair. So this is a function that allows us to construct a pair, right? And this function is already provided by the standard template library of C++, so we don't have to write this particular function. So it's already there. And then we have to give it like 2 inputs. So rank, that's the ID of the process, right? And then we're gonna need to give it another floating point number. The floating point number is actually coming from the gathered floats vector, and then we're gonna index into it using the rank ID, right? So this way we have come up with a vector that's gonna store the rank floating point number pairs, right? And if we would like to take a look at this particular pair, let's just do a printout. So for auto P that's in rank float pairs. So P is our iterator. So this is the range 4. So it's gonna iterate through every element inside of this particular vector, and every element is actually a pair with an int and a float, right? So if we want to look at the different numbers, we can actually print out a p dot first. So p is a pair. It's got a data member that's called first, right? That's the rank basically. Space and then p dot second. Right. So that's going to be printed only on rank 0. So let's take a look at if we have done this correctly. So rank 0 has a number 0.4 or 0.94 something. Rank 1 has a number 0.006 something, right? So now we have completed the third step. The second step, attach ownership information, right? So we now have a vector of pairs, and each pair is composed of the rank ID of the process and then the floating point random number, right? So that's the rank ID, the process ID, and then that's the random floating point number. So we have completed the second step. Now the third step is to sort by number. So we want to sort this vector not by the owner ID, but by the floating point, the random floating point number, right? We have to do a sort. We have to do a sort on rank 0. So how are we going to do that? We can use a standard sorting algorithm, again provided by the standard template library. So the function name is just called sort, and then we have to give it the beginning and the ending iterator between which we want to sort the objects. So rank float pairs dot begin. That's our beginning operator for this particular vector of pairs, right? And then we're gonna need our ending iterator, rank float pairs dot end, right? And then we are gonna sort of have to specify the sorting algorithm, right? Because it's not just how do we actually sort of decide which pair is actually smaller than the other pair, right? This is not automatically defined for us. What we want to do is actually compare the float, not the int, right? So we must actually specify the comparison. How do we actually define the comparison? So we want to sort of specify something that's called a comparator. Comparator is just like a function, and this comparator is going to return positive number if the first input is larger than the second input. It's going to return true, not positive number. Return true if the first input is larger than the second input, and it's going to return false if the first input is smaller than the second input. So how do we actually specify this kind of comparator function, right? We can use some construction that's called a lambda. A lambda is just like a anonymous function. It doesn't have a name, but it's something that's a function. But it's a function that can be passed to other functions as inputs. It's just like a function object. It's like a function object. You can actually pass it to the input of to pass it to sort the function as some kind of input. So how do we actually specify a lambda, right? How do we actually specify a lambda? We do something like that: a square bracket, and then followed by parentheses, an empty square bracket, and then followed by parentheses, which is for grouping the input. I'm gonna use auto pair 1 p1, and then auto pair 2, right? And then the body of the function inside of the curly bracket. So this comparator is gonna return true if p1's float is bigger than p2's float. Otherwise, it's gonna return false, right? So we're gonna return p1 dot. it's float is actually the second argument, a second number in the pair, right? So it's a second. We're gonna return p1 second smaller than p2 dot second, right? So I guess I set the logic in the opposite way. So if the float in p1 is smaller than p2, then it's gonna return true, right? If the float in p1 is larger than or equal to p2, then it's gonna return false. So that's our function. That's our lambda. That's our lambda. That's our comparator basically. Then now we can actually close this call to the sort function, right? And then um, after we have finished sorting it, we might want to sort of take a look at the pair again. Take a look at all the pairs again. Let's just copy this part of the code. Right. Let's see if we actually have done the sorting correctly. So that's the first part, right? That's without the sorting. And then that's after the sorting, right? So I should have actually printed out a separator somewhere. See out after sort. So after sort, it's supposed to so that's after sort. You can sort of see the floating point number actually keeps increasing, right? The floating point number actually keeps increasing. The biggest one is 0.8. Smallest one is 0.1 something, right? And then that's the rank. That's the owner. The owner process ID. The process ID, the rank of the owner process, right? So the rank of the owner process is also uh, sorted in a particular way based on its based on the floating point number that it owns. So now we have finished the third step, sort by number, right? And then the next step is the assign ranks by owner, right? Assign ranks by owner. How are we gonna do that? How are we gonna do that? How are we gonna do that? Right. So all those codes that I just typed so far happens only on rank 0, on the root rank. It only happens inside of this if branch, right? So we're actually doing all those kind of sorting. We're doing all those kind of rearrangement of the vector just on the root rank. So this part of the code is not executed by any other processes. It's just executed. It's just being executed by the root process, right? So we have another vector. We have another vector that was defined before. That's called float ranks. It's called float ranks. It's gonna store the ranking of the floats, of the random floating point numbers. So on rank 0, we're gonna allocate a space for this particular vector. Float ranks dot resize MPI size, and then we're gonna define a counter int I goes from 0, starting from 0, and then for auto p inside of the rank float pairs. So p is going to be an iterator that's going to range through every element inside of this vector, and every element is actually a type of pair. So this p is going to be a pair. This p is going to be a pair. So what we want to do is actually to assign float ranks. That's the float ranks of p dot first. So p is a pair, and its first data member is supposed to be the rank, right? So float ranks p dot first, we are indexing into the float ranks using the rank of the pairs, right? The first index of the first data member of the pairs. It's going to equal to I, basically, right? And then we have to increase I. And this way we have a float ranks. We have float ranks. And we're done with the fourth step. We're actually we have done with the fourth step. So if we want to actually print out those ranks, let's do another flow. So J goes from like a float ranks, and then let's just print out the cout. J separate by space, and then cout end of line. Right. So let's try to compile it, and then let's run it. So that's the float ranks. That's the float ranks. So it's got 8 numbers. The first number is actually for rank 0. It's the ordering of rank 0's number. Rank 0's random floating point number. It's supposed to be at position 5, right? It's supposed to be at position 5. So rank 0, that's rank 0, and its value is 0.75 something, and it's supposed to be ranked at position 5. So it's 0, 1, 2, 3, 4, 5, right? And then the second number is for rank 1. Rank 1, the position of rank 1's floating point number. Rank 1's floating point number is 0.6 something, and this number is ranked at 0, 1, 2. That's position 2, right? So that's why it's got a 2 here. And then the next one is for the third, the floating point number on the third rank, right? On the third rank, it's this number. It's 0.924233, and the position after sorting is 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6. Is that the right thing? I think so. I think so, right? I think so. So it's 0, 1, 2. So 2 actually is positioned at 7. Right, 2 is positioned at the last number, and then 3 is positioned at 6. Right, 6. Right. So that's the correct result. But now we have to so we have assigned ranks by owner, right? And then we have to do the last step. That's scatter all the ranks, all those numbers to the different ranks. And we're gonna have to use the MPI scatter function. We're gonna use the MPI scatter function. So on each of the all those calculations happens on just the rank, the root rank. That's MPI rank equals to MPI root, right? So on each of the individual ranks that's not the root rank, we must introduce another variable to store its own ranking, right? And it's gonna be, let's just call it float rank. So you can sort of see the difference here. So it's a float rank, right? And then there's a vector that's called float ranks. It's plural, but this is actually singular. This is just a one integer that's gonna be used to store the rank of just my own floating point number, right? So now let's call the MPI scatter function. MPI com world dot scatter, right? Float ranks. So that's the send buffer. We're gonna send this vector to. We're gonna scatter the numbers in this particular vector to each of the individual processes, right? The number we're sending out per process is one number, and then the type is integer, and then the receive buffer is just going to be this particular integer that we just sort of defined, right? But we must take its address, float rank, and then it's just one number, MPI int, and then it's coming from MPI root. That's the root process, and we're done. And if you would like to take a look at the results, let's just print out the rank, and then print out its float rank, and then end of line. So 7163245, right? So rank 0 is going to have a float rank that's 7, and then rank 1 is going to have a float rank that's 1, and then rank 3 is going to have a float rank of 6. Rank 2, I mean, rank 2 is going to have float rank of 6. So that's exactly the same as the result from the root rank, right? And that's our code. That's our code for solving this parallel ranking problem using the MPI scatter and the gather and scatter operations. Gather and scatter operations. So, um, so one of the questions you might have um, is about the syntax, right? It's about the syntax. So for now, uh, for example, if you are looking at the gather, or if, for example, if you are looking at the scatter, right? So for now, every process actually receives exactly one number for this particular diagram, right? But suppose I want root 3 to receive like two numbers, right? And then rank 2 receive like a one number, rank 1 receive like a zero numbers, that kind of thing, right? If I don't want to evenly distribute all the numbers on the different ranks, how can I actually do that, right? The same is true for gather. So suppose the the number of elements on each of the rank is actually different, and then I want to gather all those elements into like root 0, rank 0. How can I actually do that, right? And for now, all those examples we have looked at have this kind of even distribution, right? Have an even distribution of the number of elements. But suppose the number of elements is different on different ranks. How can we actually do the gather, and how can we actually do the scatter, right? And MPI actually provides another function that's called a ScatterV, and then also another function called a GatherV to address these kind of problems. And for ScatterV, the syntax is generalized slightly. It's just generalized slightly. So if you look at the user's manual, it's got more input parameters. So for ScatterV, you're still going to have a CNBuff. That's the address of the CNBuff. That's the buffer for storing all the data that's going to go out, right? And then you have another array. See, it's not exactly an int anymore. It's actually an int array. See, this cnCounts is an array that's going to be used to store the number of elements that's going to go to each of the different individual processes, right? So it's not just a single number anymore. It's an array that's going to be stored. That's going to be used to store the number of elements that's going to go to each of the different ranks. And then you still have another integer array, and this integer array is going to store the displacement, basically the offset inside of the CN buffer. The offset inside of the CN buffer. So each of the individual ranks are going to receive the data that's going to start from one of those elements inside of the displacement array, right? It basically tells you how to actually where do we want to start to send a particular segment of data to one of those ranks, right? This is also an offset array, and this offset array is actually an index into the CN buffer. It's a reference into the CN buffer, and then the data type for the CN type, and then the receive buffer. This receive buffer is going to have different length, different size on different ranks, and then receive count. Right, receive count is going to have a different number on different value on different ranks, and then receive the data type, and then the root process. So that's how you can actually use ScatterV. So let's look at another example. Let's look at another example, and see if we can actually sort of put this example into put this particular syntax into a concrete example. What I'm gonna do is to I'm gonna write a different source code. So I'm just gonna call it ScatterV. And then include the MPI.h using namespace std. Man argc chr star argv. And then init argc argv MPI finalize. And then MPI size, it's gonna equal to MPI COMM get size. It's gonna equal to and again I'm gonna define my MPI root to be the 0th rank. So so suppose we want to distribute like 20 numbers, and num equals to 20. We would like to sort of scatter like 20 integers basically. So vector int c and above, right? And then we're gonna need another integer vector to store the counts, send counts. How many numbers we want to send out to each of the individual ranks, right? And then we still need another vector to store the displacement, basically the offset, displs, the offset into the send buff, from which we want to sort of send out our data to one of the ranks. And then we also need a integer. Let's just call it n counts, right? So basically that's that's uh, that's the that's the number that's going to be received, the total the number of integers that's going to be received by each of the individual ranks, right? So now let's write the code for the root rank. If MPI rank actually equals to MPI root, right? So on the root rank we must allocate a space for the send buff because all those numbers are going to be going out from the root rank, so we must have a space for it. We must allocate a space for it. So send buff dot resize in so we want to send out like 20 numbers. So let's populate those numbers. So I goes from 0, I smaller than send buff dot size I plus plus, and then send buff I is going to have a value of I, so it's just some arbitrary integers inside of the send buff. So send buff is going to have 20 numbers that goes from like 0 to like 19, I think, right? And then we have to decide how many processes, how many numbers each of the individual ranks are going to receive, right? That's the numbers that's going to be stored in s counts, send counts, right? So s counts. So on the root rank, s counts must have a size, must have a non-zero size. We're going to resize it to MPI size, and then let's just put some arbitrary numbers into it. S counts 0. So rank 0 is going to receive 2 numbers, say, right? And then s counts 1 is going to receive 5 numbers, and then s counts 2 is going to receive 3 numbers. So I'm just going to copy and paste. Here 1, 2, 3, 4, 2, 5, 3, 1, 4, right? 2, 5, 3, 1, 4, and then I need 3 more. I need 3 more. So we're gonna use 8 different ranks. So that's why so my MPI size is gonna be 8, right? So that's why I need like 8 elements for the S counts vector. Um, so 2 5 3 1 4 2 5 3 1 4 2 2 1, right? So rank 0 is gonna get 2 numbers, rank 1 is gonna get 5 numbers, rank 2 is gonna get 3 numbers, rank 3 is gonna get 1 number, and then rank 4 is gonna get 4 numbers, right? And then we have like 8 different ranks. So when I run this particular program, when I run this particular test program, I must invoke like 8 processes. So my -amp option must have a number 8, have a parameter 8, right? That's the count. That's the count, right? So this particular vector decides each process, how many numbers, how many integers each processor is going to receive. And then we also have another vector that's the displacement, right? That's the displacement, which is basically the offset into the array, into the sand buffer, dispals. We're gonna resize it to MPI size, and then we're gonna initialize every number in the vector to 0. And then how do we actually compute the displacement, right? How do we actually compute the displacement? So the displacement is basically just the total number of integers. So the displacement for rank 0 is going to be equal to 0, right? Because rank 0 is going to start to get the numbers from the 0's offset. And then rank 0 is going to get 2 numbers. So rank 1 is going to have an offset that's 0 plus 2, right? 0 plus 2, that's 2. So rank 1 is going to have a displacement of 2, right? And then rank 2 is gonna because the rank 0 is gonna have 2 numbers, rank 1 is gonna have 5 numbers, so rank 2 is gonna get its numbers starting from offset 7. So 2 plus 5, that's 7, right? So basically that's how we are gonna compute the displacement. For auto, I equals to 1. I is smaller than dispals.size plus I, and then we're gonna dispals I is gonna equal to dispals I subtract 1 plus s counts I subtract 1. So that's gonna be the offset or displacement vector for us to actually index into the sand buffer. So once we have all those vectors, once we have the buffer, the s counts, and then the displacement vector all specified on the root rank, we can now call our before we actually do that, um, we must tell each of the individual ranks how many numbers it will be able to receive, right? So for now, this s counts information only exists on the root rank, right? So each of the individual processes still has no idea how many numbers it's going to receive, right? So before we actually call the scatter v, we must tell each individual processes or each individual ranks how many numbers it will be able to receive during the scatter v call. And how do we actually tell each individual processes that kind of information, right? We can use a scatter call to do that. So what we are going to do is to do MPI COMM WRLD. We're going to call the ordinary scatter. It's not a scatter v, but it's a scatter. The information we want to scatter is actually the s counts information. So we just want to tell each of the rank how many numbers it's going to receive during the scatter v call, basically. So the sand buffer in this case is going to be s counts. That's going to be our sand buffer, right? And then we're sending out 1 number to each of the individual ranks, and then it's going to be int. And then what's going to be the variable that's going to be used to store that particular number? To store that particular number, we have defined one number before. It's called int n count. We can just store that number in this particular variable, n count. So we're going to use the n count to as the receive buffer to receive that number. So n count, and then one MPI int type, and then it's coming from MPI root. So after this particular scatter call on every rank, every rank is going to have the information about how many numbers it's going to be able to receive during the scatter V call, right? Once it has the information about how many numbers it will be able to receive, so it can actually start to allocate its receiver buffer. So what I did is to move the n count down here to make the sort of to make this variable's definition closer to its assignment, right? So once we have this information, we can allocate the receiver buffer. So vector int receive buffer. So the receive buffer is going to have n count this many numbers in it, and then we're going to initialize it to 0, right? So now we are actually ready to do the scatter V call. Now. So how are we going to do that? MPI. I'm going to write the line first. Scatter V. So it's not a scatter anymore. It's a scatter V, right? It's a scatter V now. The send buffer, and this buffer has a non-zero size only on the root rank 0, right? On every other rank, it's just a 0 size, but it's still okay. You can put it's still okay. It doesn't matter. And then the second input is actually the count. The count vector, the count array, right? The address of the count array, basically, as counts. Again, this vector only exists on this vector only has non-zero size on the root rank, right? And then the next one is the displacement, right? The displacement vector. And then the type is MPI int. And then we're gonna need the receiver buffer. And this receiver buffer has non-zero size on every rank. That's because we have allocated space on every rank. So this line of code is not just happening on root rank, it's actually happening on every rank, right? So receiver buffer, this particular buffer has non-zero size and count. And then the number of integers that's being received on each of the rank, that's n count, right? And then the type is still int, and then MPI root. So that's our scatter V call. Right? So if we want to sort of check our results, let's just print out the receive buffer. Receive buff. Cout rank MPI rank. And I think that's everything we want to do. I think let's compile it. Let's try to compile it. So let me take a look at my source code. So scatter V, that's our source code we want to compile. So let's do MPI C++ -std equals to C++ 14-0 scatter v.cpp. Let's try to compile it. So send buff. The name is wrong, I think. It's send buff with just a 1f. So let's get rid of this. Let me compile it again. Now let's try to run it. So we must specify like 8 different ranks, right? And then scatter V. So rank 0. So it looks like I'm actually running a different code. I'm actually running the different code. Um, oh, I see. MPI run dash MP8 and then dot scatter V. Right. So rank 0 gets 2 numbers. That's 0 and 1. Right. Is that true? Rank 0 is gonna get 2 numbers. Is that true? Right. Rank 0 is gonna get 2 numbers, and then rank 1 is gonna get 5 numbers. Rank 1 is gonna get 5 numbers. So rank 1, that's 5 numbers. That goes from like 2 to like 6, right? And then rank 2 is gonna get 3 numbers. Rank 2 is gonna get 3 numbers. Rank 2 is gonna get 3 numbers. That goes from 7 to 9, right? So which means that we have done our scatter V correctly. We have done our scatter V correctly. So that's scatter V. Scatter V. So the opposite of scatter V is called gather V. It's called gather V. It's called gather V. It also has so MPI also has a gather subroutine that allows us to collect different number of um, different number of different amount of information from each of the individual processes, right? And then it also has send buff, send count, send type, receive counts, displays the offset into the send receive array basically. The offset into the receiver buffer, the receiver type root and the receive buffer. So the syntax is kind of similar. It's kind of similar to scatter V. So let's look at how we can actually do this kind of a how we can actually use this kind of function. Uh, so I'm gonna write a different source code and I'm gonna call it GatherV.cpp. Right. And then I'm gonna do MPI init and then MPI final. Nice. And then MPI size equals to and then again I'm gonna introduce the MPI root equals to 0, right? So in this example we're gonna just we're gonna create a a, a send buff on every rank, and then the numbers in those send buff are gonna be gathered to the root rank, right? So let's introduce another variable that's called ncount. So on each of the different rank, we're gonna create how many numbers? We're gonna create MPI's rank plus 1. So on rank 0, we're just gonna create like 1 number. And then on rank 1, we're gonna create 2 numbers, and then on rank 2, we're gonna create 3 numbers, that kind of thing. So that's gonna be the size, the total number of integers we're gonna put into our send buffer. So now let's allocate space. Let's allocate a space for the send buff. we're gonna call it send buff and count. That's how many integers we're gonna sort of put into the send buff. We're gonna initialize every number to 0 first, and then we're gonna put numbers into it. Although I goes from 0, and then I is smaller than n count, and then I plus plus or plus plus I, and then send buff I is gonna we'll put some arbitrary numbers into it. The number is gonna be I plus 1 multiply MPI rank plus 1, right? So that's the number we are putting into the send buff on every rank, right? So if we want to take a look at it, let's just print out some of the do auto I send buff. Okay, just do a cout rank MPI rank. Then I let's try to compile it. GatherV GatherV.cpp. Again, we are using 8 processes. So here is actually a printout of all those numbers. So rank 0 is going to have just one number, right? And that number is basically the rank ID plus 1, that's 1, right? Multiply I plus 1, that's 1 also. So 1. And then on rank 1, we're going to have 2 numbers. So that's 1. Rank 1 has 2 numbers, 2 and 4, right? And then rank 2 is going to have 3 numbers, 3, 6, 9. And then rank 3 is going to have 4 numbers. So rank 3 is going to have 4 numbers, right? Rank 4 is going to have 5 numbers. Rank 4 has 5 numbers, right? So let's comment out this printout because the output is kind of quite long, right? So we're going to need a vector that's going to be used to store how many numbers are going to be gathered from each of the process, right? Let's call it R count. Let's call it R counts. So this is going to be the vector that's going to be used to store the number of integers that's going to be gathered from each different rank, right? And this particular vector has non-zero size only on the root rank. So if my rank, MPI rank actually equals to MPI root, then I'm going to allocate a space for it. And the size is supposed to be MPI size, and then I'm going to initialize everything to 0, right? So once I have allocated space for this R counts on the root rank, I need to fill it with different values on the root rank, right? How do I actually gather all those information from each of the different ranks, right? For now, the number of integers that's going to be gathered from every rank only exists on individual ranks, right? Which is basically MPI rank plus 1, but the root rank doesn't actually know that, right? It could be just some kind of random number. It doesn't have to be MPI rank plus 1. It could be any kind of integer. It doesn't have to be follow this kind of specific rule. So how do we actually send this kind of information to the root rank so that the root rank knows how many numbers are going to be coming from each of the individual ranks, right? So we can get that kind of information by using a MPI gather, just the ordinary gather, not the GatherV, but the ordinary gather, just the ordinary gather call. And then the send buffer is going to be n count, right? So this n count has different values on different ranks. So on rank 0 it's going to be 1, right? And then on rank 1 it's going to be 2. So on different ranks it's going to have different values. So that's the send buffer. we're sending out one number, and then the type is int, and then the receiver buffer. The receiver buffer is going to be the address of this R counts vector, and it has non-zero size on the root rank, but it has zero size on every other rank, but it's okay. So R counts the address of it, and then we're expecting just the one number from each rank, and then an integer, and then we have to gather it to MPI root. So that's going to be after this particular collective call, the root rank is going to have the total number of the number of integers that's coming from each of the different rank, and those numbers are going to be stored in this particular vector R counts. Right. So in addition to that, we also need to the root rank also needs to actually know. It must know what's actually the total number of elements or total number of integers, right? The root rank must know the summation of all the numbers in our counts vector, and then it also must define the displacement, and it must allocate for the receiver buffer, right? So let's define that. So int n num, we're going to use this variable to store the total number of elements that's going to come from all different ranks, right? That's and then we are going to need a vector of ints to store the displacement, and then we're going to need a vector of integers that's going to be our receive buffer, our recv buff, right? So if MPI rank is the root rank, we must allocate spaces for it, for those vectors, right? But before we actually do that, let's try to compute n num I r counts. We're going to do a printout I separated by space, and then n num plus equals to I. So after this particular for loop, we should be able to get the total number of numbers, integers. So see out end of line, and then see out, let's total number of integers from all ranks and num. Let's just do some printout, a simple printout. Right. Now we have to sort of allocate space for the displacement vector. We resize it to MPI size, and then initialize it to 0, and then for int I goes from 1i smaller than MPI size, and then I plus I. Then all I have to do is do it the displacement vector is constructed in a way that's kind of similar to our previous example for GatherV, right? For ScatterV, dis pls I subtract 1 plus r counts I subtract 1, right? And that's our displacement vector. That's our displacement vector. And in the end, we have to sort of resize, so allocate a space for receive buffer. So receive buffer is going to be resized to n num. We're going to need this many spaces for storing integers, and then we're going to sort of initialize everything to 0. So maybe I should put this part to here. So as soon as we obtain n num, the value for n num, we should just allocate receive buffer, right? And that's everything we have to do on the root rank, right? So all those things are actually happening on the root rank. It's on the root rank. So after we have finished preparing all those vectors, we can now call our GatherV. So we're going to call our GatherV, and then the send buff So this sandbuff has non-zero size on every process, on every rank basically, right? We actually constructed the sandbuff early on, right? We constructed our sandbuff here, and then the second input is going to be the n count. That's how many numbers I'm actually sending from each of the rank, right? N count. And then the type is MPI int. So n count is supposed to be identical to the number of elements in the send buff, basically. And then I need to specify the receive buffer, the address of the receive buffer. And the receive buffer has non-zero size already on the zeroth rank, on the root rank, because I allocated space for it, right? And then, but on every other processes, on every other ranks, receive buffer is still zero size. It doesn't have any size. It doesn't have any anything. And then we need to specify the R counts vector, the address of it, and then the displacement, displs, displacement vector, right? And then the type MPI int, and then MPI root. That's it. So that's our gather vehicle. That's our gather vehicle. And suppose we want to check our results. So after this gather vehicle, if we have finished, if we have done everything correctly, if MPI rank equals to MPI root, if we have done everything correctly, then the root rank should have a vector that contains all the numbers, all the integers from every rank, and that all those integers must be stored inside of the receive buffer. Let's see if we get the right results. And that's it. That's our code for GatherV. That's our code for GatherV. Let's go back to the shell, and let's compile it, and then let's run it. So these are the printouts from earlier. So this vector is basically the number of integers that's been gathered from every process. So rank 0 is going to contribute 1 integer, rank 1 is going to contribute 2 integers, and then rank 7 is going to contribute 8 integers. So how many integers we are going to gather? We're going to gather, so if you sum all those numbers together, you're going to get 36. So rank 0 is supposed to gather 36 numbers from every other rank, right? And each rank is actually contributing a different number of integers, right? So what's going to be the results? So rank 0 is going to contribute one number, that's 1, right? And then rank 1 is going to contribute 2 numbers, that's 2 and 4. And then rank 3 is going to contribute 3 numbers, that's 3, 6, and 9. Rank 3 is going to contribute 4 numbers, that's 4, 8, 12, 16, right? And then rank 4 is going to contribute 5 numbers, that's 5, 10. So that's so receiver buffer is going to receive these 36 numbers. And that's our example. This is our example of GatherV, right? So if you have a variable, number of contributions from different ranks, you should use GatherV instead of gather, and that's our example.